Hello and welcome to another video about hypothesis testing. In this video I'll show you the intuition behind the hypothesis test, like what goes on behind the scenes. Are you ready? Well, yes you are because you're watching this video. We will begin with an arbitrary probability density function, p of x. This will represent the probability distribution for the entire population, from which we can take samples. From the central limit theorem, or CLT, we know that the distribution of the means for samples of size n from the population will form a probability density curve with a known mean and known standard deviation. Specifically, we know that the distribution of sample means will have a mean equal to the population mean, mu, as well as some known standard deviation, which we will call the standard error, or SE. So here's our distribution of sample means. We have mu in the center of our distribution, and SC as the standard error that describes the shape of this distribution. We may calculate SC, but we don't know mu. So let's get an estimate for mu by taking a sample of size n and taking the mean of the sample. In other words, we want the sample mean x bar. Therefore, we can get an estimate of what the entire probability distribution function looks like centered around the mean x bar of the sample, compared to mu, the true mean. Now let's simplify our diagram just a bit. Here we have simplified the diagram. Just remember that x bar and mu are the means of the PDFs with the same shape. Now let's introduce some arbitrary value, mu naught. We want to test whether or not mu naught is equal to mu, given only x bar and its associated distribution. In other words, imagine that mu is invisible in this diagram, but it's still there. We will test this by creating an interval around x bar. Assuming that mu is contained within this interval, then if mu naught is outside of this interval, then this implies that mu naught is not equal to mu. On the other hand, if mu naught is inside of the boundary, then it is possible that mu naught is equal to mu, since both mu and mu naught are contained within that boundary. In this case, assuming that mu is located within the boundary, we see that mu naught is located outside of the boundary, and thus we reject the null hypothesis that mu is equal to mu naught. But if this were the case, where mu naught is within the boundary, then we would fail to reject the null hypothesis that mu is equal to mu naught. But how do we know when mu is located within the blue interval? Well, the answer is that we actually don't know. But what we can do is get the probability that this will be the case. Let's now focus our attention on just the components of the diagram below. In our diagram, depending on the value of x bar, mu can either be located inside or outside of the blue interval. For the purpose of the following argument, we will say that the radius of the blue interval is equal to r. We can see here that the minimum value of x bar, such that mu is located within the blue interval, is mu minus r. And the maximum value of x bar, such that mu is located within the blue interval, is mu plus r. So what is this red interval that we just created? That is a confidence interval around the true mean mu. This means, for example, that if we choose r such that we form a 95% confidence interval, then mu will be contained within the blue interval 95% of the time. This implies that our hypothesis test will work properly 95% of the time. Alright, so that's the end of this video, and thank you for watching.